What if the same technology powering your smartphone could unlock the next great revolution in computing? That's exactly what a London-based startup just unveiled. The world's first full-stack quantum computer built entirely with regular silicon chips. Forget exotic materials or futuristic labs. This machine was manufactured using the same process behind everyday electronics. Today, we'll break down how this breakthrough works, why it matters, and whether it could finally push quantum computing into the mainstream. Quantum computers aren't just faster, they're fundamentally different. A classical bit is either 0 or 1. A quantum bit, or qubit, can exist as 0 and 1 at the same time. Superposition. Even more powerful, qubits can be entangled, meaning they share states across distance, so changing one instantly changes the other. These properties make quantum systems capable of solving certain problems like drug discovery or cryptography millions of times faster than classical computers. But here's the catch. Qubits are fragile. Tiny vibrations, stray electromagnetic waves, even a small temperature shift can cause them to lose their quantum state, a phenomenon called decoherence. This fragility has kept quantum computers mostly trapped in labs with huge, expensive refrigerators and exotic materials. Until now. Enter Quantum Motion, a UK startup that has done something extraordinary, building a quantum computer using CMOS technology. That's complementary metal oxide semiconductor, the exact same process used to make chips for laptops, cameras, and smartphones. Why is this huge? Mature tech. CMOS fabrication is one of the most advanced, standardized manufacturing processes on Earth. Energy efficient. CMOS chips consume virtually no power when idle. Scalable. Billions of these chips are already mass-produced annually. The entire system fits into just 3 19-inch server racks. Inside are the Quantum Processing Unit, QPU, integrated control electronics, and a dilution refrigerator, all working together to keep qubits stable at near absolute zero. And here's the real kicker. The computer doesn't just have the hardware, it's full stack. That means it comes with industry-standard software tools like Qiskit and Cirq, making it far easier for researchers and developers to run real-world quantum programs. The machine uses spin qubits, storing quantum information in the spin of individual electrons. Unlike superconducting qubits or trapped ions, spin qubits are small, energy-efficient, and, most importantly, built with silicon. Quantum Motion has also designed the QPU using tile architecture. Think of it like Lego blocks. Each tile contains everything needed for compute, readout, and control. Want to scale up? Just add more tiles. In theory, this design could expand to millions of qubits. This announcement has been compared to the early days of silicon chips in the 1950s and 60s, the moment computing shifted from vacuum tubes to transistors. Here's why this could be just as transformative. Cheaper production. Leveraging existing semiconductor fabs avoids reinventing the wheel. Rapid scaling. Modular design plus global chip supply chains equal faster deployment. Data center ready. The form factor means it can fit where today's servers already live. Integration potential. Silicon-based quantum systems could one day sit alongside classical CPUs and GPUs in the same facility. The system is already installed at the UK's National Quantum Computing Centre, NQCC, part of a government-backed program to test multiple quantum technologies side by side. Quantum Motion's approach builds on research with University College London, UCL, where they achieved 98% accuracy in 2-qubit gates, the fundamental operations of quantum circuits. That's a world-leading result for silicon qubits on a 300mm wafer. But why is this so important? Fault tolerance. Quantum error correction is essential because qubits are unstable. The more accurate your gates, the fewer extra qubits you need to correct errors. Silicon's natural advantage. We already know how to manufacture and control it at scale. The company is also part of the CC project, Silicon Quantum Error Correction, working on architectures that could scale to millions of fault-tolerant qubits. Now, let's not get ahead of ourselves. Quantum Motion hasn't yet released detailed benchmarks, coherence times, total qubit counts, or system error rates. Even with silicon, quantum error correction requires enormous overhead, sometimes thousands of physical qubits to make one logical qubit. Cooling remains non-trivial. Dilution refrigerators are complex and power-hungry. Competing platforms, superconducting qubits, trapped ions, photonic qubits, are also advancing fast. This is an amazing milestone, but it's also a reminder. Quantum computing isn't a sprint, it's a marathon. The winners will be those who can scale, correct errors, and integrate with the real world. If silicon quantum computers succeed, the implications are staggering. Drug discovery and healthcare, simulating molecules at atomic precision. Climate modeling, predicting complex weather and energy systems. Logistics and finance, solving optimization problems too big for today's supercomputers. AI acceleration, training large models more efficiently. With silicon as the backbone, quantum computers could move from experimental labs into everyday data centers, maybe even into your home devices decades from now. This could be the beginning of quantum computing's silicon revolution, the moment we go from fragile lab prototypes to something that can be built, scaled, and deployed worldwide. Of course, the road is long, but breakthroughs like this bring the future closer than ever. What do you think? Will silicon-based quantum computers dominate, or will other technologies win out? Drop your thoughts in the comments. I'd love to hear your predictions. If you enjoyed this deep dive, don't forget to hit like, share this with a friend who geeks out on tech, and subscribe for more explorations into the future of computing. Until next time, stay curious.